Okay, so today we're going to have a look at a three-phase cable calculation for a direct online starter. So I've done all the calculations and I've put them into this table which we can go through. We've got our supply characteristics, we've got our circuit description, types of cable we're going to be using, reference methods, preliminary volt drop, we've got our correction factors, we're going to be calculating IZ, we're going to do our volt drop, we're going to check our fault current, we're going to do the adiabatic and thermal withstand calculations, and we're going to calculate ZS. This is still a basic cable calculation, but trying to introduce some new elements to it, the three-phase and such. An entirely theoretical setup. It's not a video on how to install motor controls at all. So we have our main distribution board, then we have three-phase switch fuses off it, and each switch fuse goes to a direct online starter, which controls the motor. Direct online starting is one of the simplest ways to control a motor. You're putting power directly onto the motor. You haven't got the more complex controls like star delta starting. This is just basically a simple on-off button. But this can cause issue, which we need to consider at the beginning of our calculations, what type of protective device we're going to use. So one of our basic principles is automatic disconnection of supply, ADS. We want the protective device to operate within a certain time to remove any danger. Problem is, our protective devices often can't tell the difference between a sudden spike, an inrush, or a fault. So the starting current for this motor could be 8 times its full load current. The protective device might see that as a fault, which would obviously be a nuisance. So you've got to consider what type of protective device you're going to use. If you're using the 60898 type devices we're all familiar with, they can be very sensitive. You get different types of circuit breaker, types B, C and D. These are trip curves for them here. The tripping is basically 5 times the rated current, 5 times for B, 10 times for C, and up to 20 times for type D. So if you're installing a motor, you might want to think about using the type D circuit breaker. Issue with that though is, look at our earth fault loop impedance. A maximum earth fault loop impedance is 1.09 ohms at 70 degrees, 0.88 at 10. So that's going to have a bearing on the length of run or the size of cable we choose. Or you might decide to go for a fuse, your BS88 type fuse. And if you look at the maximum earth fault loop impedance, this is for a 10 amp fuse, it's 4.65 ohms. So you've got a little bit more leeway there, haven't you, in your design of this circuit. In this theoretical example, I'm going to be using the BS88 fuses. So let's start at the beginning. So we need to know our earthing arrangement. In this case it's TNCS. What the voltage is. This is three-phase. There's 2 voltages listed. UO, that's voltage to earth, and U, that's voltage between the phases. So it's 230 and 400 volts. In this case we've got a ZDB. This is a distribution board and it's not the origin of the supply. We've got a very low ZDB of 0.08. So we're obviously quite close to the transformer. We've got our perspective fault current. You can get various different values for this depending on how you calculate it. If you use the rule of thumb where you test between a phase and neutral and times it by 2, you're going to get a high perspective fault current. You can actually measure it. Or you can measure between the phases and divide by 0.87. Various different methods for getting your perspective fault current. And the power of the circuit that we're installing, 4.5 kilowatt 3-phase induction motor. We're taking a feed from a switch fuse to a direct online starter, which is directly adjacent to the motor. The installation is on perforated tray. We have an ambient temperature of 40 degrees C, and it's grouped with 2 other circuits. We're going to install a 4-core 90 degrees C SWA cable. We'll come back to the 90 degree. This example I've chosen a 4-core cable because we're installing a 3-phase motor, so we don't need a neutral, but you might want to take a neutral to the location. 3 cores for the 3 phases and 1 core for the CPC. Or you could use the SWA as the CPC and the other core could be for a neutral. Just depends how you utilise the cable. The table that we're going to be using for our calculations is table 4D4A. We're going to be using reference method E, which is column 5, installed on perforated tray. The length of the run is 30 meters and the power factor is 0.8. So the calculation for design current, which is our IB, we're going to times the motor kilowatt rating by 1000. So that's 4.5 times 1000. The bottom line, we've got the square root of 3 times U times PF, power factor. U is 400 volts, that's between the phases. PF is 0.8. And so you just put those numbers into the calculator. But you want to be a little bit careful here. You really want to square root the 3. You're not square rooting the voltage and the power factor as well. I've sped this up a little bit, but as you can see, the first time I do it, I'm only square rooting the 3. You notice the second time I do it, I've square rooted the whole of the bottom line, the voltage and the power factor, and you get a vastly different number. So anyway, we have our design current, which is 8.11 amps. And now we've got our design current, we can choose the rating of our protective device, our IN. IZ has to be greater or equal to IN, which has to be greater or equal to IB. So our protective device has to be at least equal or greater to IB. So with a design current of 8.11 amps, the next protected device rated higher than that will be a 10 amp protected device. Because this is a motor circuit, we're going to be using BS88 2-type fuses, which can handle the potentially large starting currents of motors. So we have our IB and our IN. Now we need to start thinking about what cable we could use. Further on down the line, we'll be checking our volt drop to make sure that the cable is acceptable. Now we can do a preliminary step first, so we're not wasting our time choosing cables that ultimately will not be satisfactory. So our design current in our IN is going to give us an indication of what size cable we'll be choosing. We can use this preliminary step to get a millivolt per amp per meter value. This is it here, millivolts divided by the design current times the length. Let's have a quick look at volt drop though. Volt drop is what it says it is, it's a drop in voltage from the origin to the furthest point of the circuit. The impedance of the cables will cause a drop in voltage, and because our lighting and power circuits require a certain voltage to work correctly, we don't want that voltage to drop too much, so we have limits. On the consumer side, the regs tell us 5% for other circuits and 3% for lighting. There's also the distribution side as well. There'll be volt drop in the distribution cable, so the volt drop is from the transformer to the furthest point. Some people are in control of volt drop at the origin, most of us aren't, so we work within the final circuit section. So our origin will be our supply terminals. The Electrical Safety, Quantity and Continuity Regulations 2002 tell us our voltage range, 230 volts plus 10% and 230 volts minus 6%. So we have a range of 253 to 216.2 volts. Voltage is always fluctuating, but you have to pin some numbers on it. These numbers are from the design guide, and for calculation purposes, 9% used in distribution and a conservative 4% final circuits. So 23 volts lost in distribution, 9.2 volts maximum lost in the final circuits. And again, from the design guide, 5% of 400 volts is 20 volts line drop. To get the single phase, it's 20 divided by the square root of 3, which is 11.5 volts. So we'll use 20 volts in our 3-phase calculations. So as mentioned, we can split our volt drop into sections. We have the distribution side and then we have the installation side. And on the installation side, we can split that again as well between any switch gears. In this installation, we have 2 sections. We want to know the volt drop in the cable from DB1 to DB2, and we want to know the volt drop in the cables from DB2 to the motor, our final load. These are both 3-phase volt drops, but you can get combinations. It could be a single phase load off this as well. And because in the regs our millivolts per amps per meter, we get different values for single phase and 3-phase, you can't really directly add the volt drops together. So what they recommend you do is do it as a percentage. So this is the millivolt calculation for the cable from DB1 to DB2. We get a volt drop of 1.2 volts. Now, if we work that out as a percentage, 1.2 volts divided by 400 times 100 is 0.3%. So this section of cable from DB2 to the final load, these are sums here, we get 6.08 volts, and 6.08 volts is 1.52%. Now we can add those together, we get 1.82%. 1.82 is below 5%, so we know that we're in the correct volt drop range. So back to the preliminary check. So the maximum amount of volt drop we can have is 5%. It's not a lighting circuit, which on a 230 supply is 11.5 volts. 3-phase is 20 volts. From dB1 to dB2, we had a volt drop of 1.2 volts. We just want to work out the cable from dB2 to the final load. So we'll ignore that 1.2. So 20 volts minus 1.2 times 1000 divided by the design current times the length, 30 meters, will give us a millivolts per amp per meter of 77.27. Now that's quite high. It is a relatively low design current. Any cable with a rating less than that is potentially suitable. We haven't done our correction factors yet though. This is just preliminary. And when we look at our tables, 4D, 4B, make sure that we're looking at column 4 because that's for our 3-phase. So our suggested millivolts per amps per meter would be 25, which is a 1.5 millimeter squared cable. And if we look in column 5, reference method E, we've got an IT of 19 amps. This is just a preliminary suggestion. We've got to do our correction factors yet, but it is a useful preliminary step, so you're not wasting your time choosing unsatisfactory cables. This would be a good time to consider how often the motor is going to be stopped and started, because our dull starting currents can be up to 8 times the full load current. That can have a heating effect on the cable. The cable hasn't got time to cool down between switching events. This can become very involved, but the basic suggestion is to times the full load current by 1.4. In our case, we had a design current of 8.11 amps times 1.4 equals 11.35 amps per phase. And this is a consideration when we come to choose our IT. So let's get on to correction factors. We have correction factors for ambient temperature, grouping, thermal insulation, if you've got a rewirable fuse, the depth of burial buried in the ground, and for the thermal resistivity of the soil. And we either divide the design current or the rating of the protected device by any of the correction factors that the cable is subject to, so we can calculate what the current carrying capacity of the cable ultimately needs to be. If we're in a high ambient temperature, our cables are grouped together, or they're going through insulation, those cables find it harder to lose their heat, and so the copper conductor will increase in temperature, and with an increase in temperature you get an increase in resistance. And with an increase in resistance you might start having issues with your earth fault loop impedance, your disconnection times, cable might overheat. We want to stop our cables getting above their maximum operating temperature. So in our situation here, we've only got 2 correction factors. We're in a high ambient temperature of 40 degrees C, and we're also grouped with 2 other circuits. And BS7671 gives us various factors, which we either divide or times by, depending what you're doing. Generally, you divide by them. So we've got our ambient temperature factor of 0.87. That's because we're at 40 degrees C. We have a grouping factor of 0.82, and these will all derate the cable. And we have to consider, is overload protection required? If overload protection is not required, you can use the IB, the design current. But because this is a motor, and a motor can stall, it can overload, so we do need overload protection. You've actually got overload protection to direct online starter. You don't necessarily want the fuse to be operating though because of an overload on a motor. The overload in the direct online starter will deal with motor overload. We're still going to calculate the overload protection is required. We're going to use IN. So we're going to divide IN by our correction factors for ambient temperature and grouping. This will give us a value for IZ, for which we can choose our IT. IZ is the current carrying capacity for the cable under continuous use, and IT is the tabulated values we look up in BS7671. So here, our protected device IN was 10 amps, and we're dividing that by 0.87 times 0.82. These factors occur at the same time, so we include both of them. Any of the factors that are not involved, we can either times by 1, or just ignore them, don't put them in. We get a value of 14.01 amps. Now this cable isn't carrying more current. We've got our design current, that doesn't change. But the cable has to be rated as if it was carrying 14.01 amps. So this 14.01, our calculated IZ, has to be greater or equal to IN. And our IN was 10 amps, so IZ is greater. And our IT has to be greater or equal to this value. We now need to look at the tables in BS7671 and find a cable that can carry 14.01 amps for this particular set of circumstances. So here we have table 4D4A. We've used reference method E, and we want to use column 5. It's a 3 or 4 core cable, 3 phase. Remember, we're looking for a cable that can carry 14.01 amps. 1.5mm squared cable has an IT of 19 amps. That is above our calculated value. Looks like it's going to do the job. So our preliminary calculation seems to have suggested the correct cable, and we know that our volt drop is going to be alright, but we still got to do the volt drop calculation. So this is the formula for our volt drop: millivolts per amps per meter times design current times the length of the circuit divided by 1000. Dividing by 1000 to get from millivolts to volts. So that's 25 times 8.11 times 30 divided by 1000. And that gives us a volt drop of 6.08 volts. Maximum volt drop for 3 phases 20 volts. So volt drop on this circuit is good. So the equivalent voltage drop in line voltage is square root of 3 times 6.08, which is 10.53 volts. If the 3-phase circuit is not a balanced load, I reckon each phase should be calculated as a single phase circuit. So what we need to start thinking about now is our adiabatic and our thermal withstand calculations, making sure our CPC is correctly sized, and also making sure our live conductors are suitably sized. Now, to do these thermal calculations, we need to know what sort of fault current we're going to be getting in this circuit. Fault currents need careful consideration. This video is not going to go into the various measurement categories and tools to use. Basically, the closer you are to the transformer, the higher the fault current is going to be. This fault current can be absolutely catastrophic, but it's just as lethal at the load. Some fault current calculations need a high level of skill and understanding, such as when you're calculating arc flash, which will require specialist training. But we need to do our basic fault current calculations. Sometimes you have to measure fault current. That's when you have to be extremely self-aware and know exactly what you're doing. Now, fault current can become a bit complicated. Basically, we want to make sure that any fault current is interrupted before any damage to the installation can happen. And we have minimum and maximum fault currents. At the origin of the installation, this is where we would expect to find our maximum prospective fault current. And this maximum fault current is most onerous for the protected device. We want to make sure that the protected device can interrupt the fault current and not be damaged by it. But also at the load end, we want to make sure that there's enough fault current to actually operate the protected device. Our minimum prospective fault current would be expected here. Usually ZS, but we've got to think about the neutral as well. And this is the most onerous for the cable. Long disconnection times and low fault current can have a heating effect on the cable. As can be seen here, the energy let through of the protected device is actually higher for lower fault currents and longer disconnection times. We're going to be covering energy let through with I2T in a separate video. Appendix 14 of BS 7671 gives us some information of determination of prospective fault current, and prospective fault current should be determined at every relevant point of an installation. Relevant points being switchgear, protected devices, and the devices have to be able to withstand that fault current safely and protect downstream equipment. In a 3-phase installation, the highest prospective fault current occurs with a simultaneous fault between all line conductors. An approximation of the prospective fault current between line conductors can be determined by a measurement between a line conductor and neutral multiplied by the square root of 3. And an approximation of the prospective fault current due to a simultaneous short circuit fault between all line conductors is determined by a measurement between line and neutral multiplied by 2. This errs on the side of safety and will give you, in some cases, quite considerably larger fault current than will actually happen. There's more accurate ways of checking for fault current, so it can get quite involved. These formulas are a video within themselves, so I'll put these up and you can pause and have a look through them if you want to. They're very interesting. It's all basically Ohm's law, but there's lots of individual elements, mainly to do with impedance and reactance and such. They are from older but still excellent publications, but maybe missing recent updates such as CMin, CMax. I do find these give me a good understanding, and cross-reference with more recent publications, you get the full picture. The electrical installation design guide gives some good information. A lot of it is for larger installations, but they do cover smaller installations as well. This is taken from a section on calculating maximum fault current, which I do say is for large installations. IPF, maximum fault current, V equals UOC divided by ZX plus ZD. UOC is open circuit line to neutral voltage. ZX is phase impedance of transformer or supply. And ZD is the line impedance of the distribution cable. Then we have this formula here, and this is to calculate the minimum fault current. And if you look at it, basically voltage divided by the ZE plus the R1 plus R2, which basically brings it down to VIR. Voltage divided by resistance gives current. This is a bit unusual because we've got correction factors for the external. We're not in control of that normally. We can apply correction factors to our R1 plus R2 and such. Don't normally do that to the ZE. Some people do have private transformers, so they do have control over the external as such supply. So it's ZE at the origin, ZS at the furthest point from the origin, and if there's a distribution board or something in between, that would be your ZDB. To get our perspective earth fault current and our maximum earth fault loop impedance. And we measure or calculate or inquire about our maximum perspective fault current at the origin, or we can measure or calculate our minimum perspective fault current at the load end. If you inquire, the DNO will always give you the worst case scenario. It might say something like 16 kiloamps, and you'll think, hang on a second, my MCB is already rated to 6,000. You'll have a BS8083 or such fuse before your MCBs. So the DNO service fuse will be able to handle up to, say, 33,000 amps, and that protects the downstream circuits. That's why you can have an MCB with a 6,000 breaking capacity, because it's protected by the upstream device. It's known as selectivity or cascading. So to get our ZS, we need to know our ZE, or in this case ZDB, and our R1 plus R2. That's a resistance or impedance of our line conductor and our CPC. R1 is a line, R2 is a CPC. And there's tables in the on-site guide and such that give us a value of resistance in milliohms per meter for our conductors. We've got 1.5 millimeter squared conductors. This is SWA cable. So all the conductors are the same size, not like twin in earth where the CPC is smaller. We can get an R1 plus R2 value of 24.2. Now we times this 24.2 by the length of the circuit, 30 meters, and divide by 1,000 to get from milliohms to ohms. But this 24.2 milliohms per meter value was at 20 degrees C. We need, because we're calculating, we need to know what this will be at 70 degrees C to see if it's still acceptable. So we have a correction factor of 1.2 that brings it up to 70 degrees C. This is the maths here. Our R1 plus R2, which comes to 0.72. We times 0.72 by 1.2, and we add on a 0.08. We get a final value of 0.94. ZDB plus R1 plus R2 equals our ZS, and we have a value of 0.94 ohms. So now we can calculate our fault current. Fault current is basically voltage divided by your ZS. We've also got a correction factor with this. Cmin is a factor that deals with voltage fluctuation in our installations. Voltage can fluctuate between 218.5 volts to 253 volts, and depending on what you're trying to calculate, you use either Cmin or Cmax. Cmin is 0.95, Cmax is 1.1. So our fault current is 230 times Cmin 0.95. Basically that brings the voltage down to 218.5 volts. So 218.5 divided by 0.94 will give us 232 amps. So that's how much fault current can flow in our circuit. Or is it? This is our fault current line to earth. We could have a fault current line to neutral, we could have a fault current phase to phase, or we could have a fault current across all three phases. This being SWA, the CPC is the same size as the neutral, but the CPC in twin and earth has generally got a smaller cross-sectional area than the live conductors. Or you could be using the armour of the cable as a CPC, or indeed you could be running a separate CPC entirely. So we have to take that into consideration. So we have to decide which fault current we are going to use. The adiabatic equation S equals square root of I squared T over K, that is sizing the CPC. Thermal withstand is to confirm that live conductors won't reach their maximum operating temperature before the protected device operates. And in a three-phase, three-wire setup, you haven't got a neutral conductor, so you're going to have to use the phase-to-phase for your thermal withstand. So back to these three different fault currents here. These are the approximations in BS7671. Like I mentioned, you can get more accurate fault currents. These will give you larger values. But it's important to remember that these are the fault currents at the actual load. And these fault currents are lower because we've got some impedance between the supply and the load. The fault current will be a lot higher at the origin. And as the cable gets bigger, you'll also have some reactance as well. So these are our minimum fault currents. We also need to know our maximum fault currents. Our maximum fault current at the supply. And once we confirm that our protected devices can withstand the energy that could flow in a fault, we don't have to confirm the maximum energy further down the line. We need to confirm the minimum amount of energy that will flow to operate a protected device. Now we have our fault current, we can see if our CPC is correctly sized by using the adiabatic equation. So the size of our CPC is the square root of I squared T divided by K. I squared is our fault current squared, time is how quickly the protective device will operate, and K is a factor we get from BS7671. And again, we've got to be careful with our square root here. We're only square rooting the top line. We're not square rooting the 115, the K value. So our fault current was 232 amps squared times 0.1. 232 amps will cause this protected device, the BS88 fuse, to operate within 0.1 of a second. Well, if you look at the graph, a 10 amp fuse only needs 60 amps for 0.1 of a second. We've got over 200. You're probably looking at times of 0.01. BS7671 only gives times up to 0.1 of a second. If you want to get the true characteristics of these protected devices, you have to look at the manufacturer's data. So back to the adiabatic. So the square root of 232 squared times 0.1 divided by 115 will give us 0.63 millimeters squared. That's our size. There's no conductor, 0.63 millimeters squared. This is our minimum conductor size. So we'll go up to the next size, which is 1 millimeter squared. Now we've got 1.5 millimeter squared SWA. So the conductor we're using for the CPC is 1.5 millimeter squared, which is obviously bigger than 1 millimeter squared. So according to the adiabatic, our CPC size of 1.5 millimeter squared is acceptable. But what about our live conductors? We need to know that they won't go over their final temperature before the protected device is operated. So we do the thermal withstand. This time we're looking for time. So K squared times S squared divided by I squared. And we get a time of 0.55 seconds. That's for the fault current between live and neutral. We haven't got neutral, so we need to use the phase-to-phase fault current. And in the basic example, that's 402 amps, which brings our thermal withstand down to 0.18 seconds. But because that's a higher fault current, it's going to trip within 0.1 of a second, or like 0.01 of a second. So the protected device will operate before the final temperature of the cable has been reached. It's something I'm not going to go into in this video, but there's a video coming up very shortly, which I think is going to be good. I've got somebody helping me. A chap called David Betteridge, and he's got some great ideas for some videos. Looking forward to work with him. We're going to discuss energy let-through of devices. So protected devices don't actually let through such a large amount of fault current. We've got a bit of backup safety in all this, but that's for another video. So from this switch fuse here to the 3-phase induction motor, a run of 30 meters. In this certain set of circumstances, 1.5mm cable is acceptable. Don't forget that's 3 times 1.5mm square cable. It's a 3-phase motor. There's one of the benefits of 3-phase. You get more power and you don't need such a large cable. A couple of things to mention as well. The SWA you'll be installing will be 90°C SWA. Don't think you can get 70 anymore. We've still got to do the calculated values to 70°C because a lot of our isolators and switches and such are only rated to 70°C. Anyhow, I'm going to come back to this quite a bit because I've got some more stuff on direct online starters. I've got some more notes on that cable calculation we just did, but I think I'll put that onto another video. Very well done if you managed to get this far. And as always, thanks very much for watching.